All right, so that's prompt injection. And there's a bunch of that you can do, and a lot of people like it. It's basically social engineering for computers. It's not about anything technical, but there's a lot of other things to do, and let me show you that. We can get into more technical machine learning stuff, and now you can also take Google Learning. There are courses you take where you learn the concepts, which are nice. You get absorbed that way, although I don't think this is a place where people want to do that. And there are some challenges here just to see if you understand the concepts of the OWASP things and the Microsoft Copilot security. That's sort of like reading term education stuff, but the hands-on stuff starts down here. So let's start with the 100. Now, the cool thing here is all you need is a Python environment, and what I like to use is Google Colab. This is great because you do not need to have any Python installed locally at all. You use a free Google environment to do your programming in, and all you need is a Google account. So here I am. I got to sign in with one of my Google accounts, of which I have a bunch like everybody else, I suppose. All right. And by the way, you might need to use a personal one because your college or whatever might have turned it off. But anyway, now that I'm in, I make a new notebook, and I've got a cloud Python environment, which is why we don't need a lot of bandwidth here. You don't need to download anything. So now you can execute Python code here. And by the way, you can execute Bash shell code by just putting an exclamation point in front of the lines. So the first thing you need is you need a library, because the reason Python is easy is because other people have done all the work. All you have to do is find the right library and figure out how to use it. So TensorFlow is one of the libraries you can use for machine learning. And so this is just going to import it and then print a version number, and I don't really care what version it is, they're all fine. So we're going to do a simple machine learning task. I used to do physical science, and so if you measure something like pressure and temperature, you vary something like the temperature in X, and then you measure something like the pressure and see how it changes. So here's a pattern of an independent variable and a dependent variable. So as you can see, there, when X goes up, Y goes up. And if you look more closely, you can see when X goes up by 1, Y goes up by 2. And when X is 0, Y is minus 1, so the relationship is Y is 2 times X plus 1. Now, in traditional coding, it requires a human to do that thinking. Only a human has the intelligence to detect that pattern. But in machine learning, it's going to figure out that pattern. And it only takes about 10 lines of code to do it. So this is going to make a single neuron machine learning model. Here, add another block of code and put in that stuff. And what's going to happen is, here's the data. Here's X going minus 1, 0, 1, 2, and here's the Y going up. And it's going to fit that model. Now what it's going to do is use the simplest technique of all, which is gradient descent. You measure the error, and by default it uses the sum of the squares of the vertical errors as a measure of how bad the fit is, and it figures out what direction would I change the parameters to make the error go down. And it takes a small step in that direction, because to determine the direction it uses partial derivatives, which assume that the thing is locally linear. And pretty much everything is locally linear if you make a small step. So it's like a ball rolling down a hill. It moves in the direction that is currently the steepest slope, and then a little bit, and then a little bit, and a little bit, and it's going to do hundreds of steps into the gradient descent. So there it goes. It started out with random parameters, so the loss was 22, which is the error, which is really big, but then it moved down to, and the loss keeps going down and down, because each step it can figure out which direction will improve it, and it takes a bunch of steps, and after 500 steps, it gets down to a much lower loss, 0.007, 0.001. The loss is getting down to essentially 0, like 10 to the minus 4, because this is perfect data with no noise. In fact, if you get Y equals 2X plus 1, it will 100% fit everything. So the loss gets down to almost 0. Then it's complaining about something. I'm not going to worry about it. That's what's causing that error. We're going to go ahead. This is what this model is. It's a single neuron, and all it is linear. It takes the input, multiplies it by M, and adds C. And it's just trying to find these numbers. So the next one, I'm going to print out the results, and I'll just try running this one. Previous one gave me some kind of funny error, but I assume that's not important. Let's see how this one works. All right. This does the same thing again, but then it's going to print out the answers for the slope and intercept at the bottom, so we can more easily tell whether it's working. So there it is, going through the epochs of training. And as you can see, it doesn't take long. It's taking like 50 milliseconds to do each step, because this is, of course, a very simple neural network containing only one neuron. Not much to be, and only maybe 6 or 7 points to calculate the least square, so it's really not doing very much here. And let's see what it comes up with. All right. And now it's complaining, which is rude. Here's what I learned: get weights, unrecognized data type, x equals 10. All right, I think I need to not put brackets around the 10, which is something has changed here. But let me just get that line. If you hit this problem, you don't really need this to get the flag, but anyway, here, I think it's that stuff. For some reason, you don't need brackets around the 10 anymore, although you used to, as recently as like a week ago when I taught this class. So this is another thing that's fun. The libraries do all the work for you, but they keep changing the libraries for things like this. And it doesn't like that either. All right. I'm not going to worry about it right now. The point is, it did pretty well when I did it before. See, the two numbers that were supposed to be 2 and 1 were 1.99 and minus 0.99, so it solved it very well. So now, you've got some challenges here. The first one is add some noise to it and see what happens. And the noise means, of course, the error will not get so small. Then you can try fitting something that is not a straight line. Here's a parabola, and when you try to fit it with a straight line, of course, it's not going to work very well. You're going to have a really large error. But then you can try fitting a complex curve, and this one is more fun. You're going to make a proper neural net. You're going to have an input layer of neuron that takes X, the input data. Then you're going to pass it to a layer of hidden neurons, and another layer of hidden neurons, richly connected. So these will process the data, and these will process the data more, and then you go to one output neuron. And this is what I was describing earlier about interpretability. This might learn to fit the data, but you don't really know what these neurons are doing. Where each line touches, you have two parameters, a slope and an intercept. So there's a lot of parameters here. And so if you don't like what it's doing, you might say, well, should I change the weight here to be smaller? Would that make it stop doing the bad thing? And the answer is nobody knows. Just like in the human brain, they say, well, which brain cell is making you bad? You know, which one do I cut out to make you a good person? And we don't know because it's too complicated. But anyway, here's the code for that. Let me see if this one's going to run. And if not, then I'm going to have to figure out how to load an old version of the libraries or something. Let's see how this one looks. All right, so there it's created the model, and I can tell it's a new version because they're formatting this differently. So probably specifically loading an older version of the main library would get rid of these problems. And that may be necessary for all of these. We'll see. So here it is, going through its epochs. Oh, good, it worked. Okay, good. And so this one here, as you can see, it did a pretty good job of fitting that data. Of course, that's not too surprising because it has an awful lot of parameters. And if you want to see how many parameters there are in this model, you can go to the diagram here. This shows you the first layer is one, that's the input neuron. Then there's 64 neurons in the next layer and 64 in the next layer. These are the hidden layers. So a number of parameters is 2 here, slope and intercept, 128 for here, 64 times 2. Here, 2 times 64 squared. Each one of the 64 goes to all the 64 in the next layer. So 4,000 parameters here, 65 there, for a total of 4,355 parameters here. So that's enough to fit a very complicated shape, and it did a pretty good job of fitting this shape. So for the challenges here, you can try changing your model to try different ones. Try adding just one layer of 64, then try adding things like 2 layers with 32 units, 16 units, 4 units. See which of these combinations is most successful. And then you can try changing the amount of noise and such. Change the amount of noise, see how it fits, that sort of thing. So this gives you an idea. You can start seeing how to fit this data with Python. So I'm going to stop this recording.